Today we're going to discuss computing square roots. First, let's recap some ideas from before. Let's say that we have a complete ordered field F. We'll consider the following map, which takes a number t from our field F, and it'll return a point xy that's on the unit circle. Here's a graphical representation. On the left, you can see the number line, which corresponds to the field F. And on the right, you can see the unit circle, which corresponds to this notation we have above, S superscript 1, parentheses F. In this way, we can think of an element t sub n as a point p sub n on the circle. In particular, the Euclidean distance between 2 points p sub m and p sub n can be expressed in terms of the absolute value t sub m minus t sub n. This means that the 2 points p sub m and p sub n are close together, that is, the Euclidean distance is small, if and only if the absolute value t sub m minus t sub n is small. Similarly, we can think of the number infinity in our field F as corresponding to the north pole, namely the point 0, 1 on the unit circle. In particular, you have the Euclidean distance p sub n minus the point capital N, which can be expressed in terms of the reciprocal of the square root of t sub n squared plus 1. This means that the 2 points on the unit circle, p sub n and the north pole, capital N, are very close together, if and only if the absolute value of t sub n is large. This motivates the following definition. We'll say that a sequence t0, t1, t2, and so on converges if given any positive epsilon, we can find a delta such that the distance between p sub m and p sub n is less than epsilon whenever m and n natural numbers are greater than delta. We'll come back and discuss this a bit later in our future lessons. Otherwise, we'll say that our sequence does not converge. We also discussed the concept of a monotone sequence. Again, say that F is a complete ordered field, and say that we have a sequence capital A, x0, x1, x2, and so forth. We'll say that our sequence is monotone increasing if xn plus 1 is greater than or equal to x sub n. We'll say that our sequence is monotone decreasing if xn sub 1 is less than or equal to x sub n. We'll say that our sequence is monotone if it is either monotone increasing or monotone decreasing. The celebrated monotone convergence theorem, simply put, says that a monotone sequence converges. We'll explain by discussing a few different cases. First, say that we have a sequence that is monotone increasing. If the sequence has an upper bound, then it converges. If the sequence does not have an upper bound, then the sequence just increases without bound. Now say that our sequence is monotone decreasing. If the sequence has a lower bound, then the sequence converges. Otherwise, the sequence decreases without bound. We also discussed a couple of different examples. First, let's consider an arithmetic progression. That is a sequence of the form x sub n is x0 plus nb, where b does not equal to 0. Since we know that the difference of consecutive terms, namely x sub n plus 1 minus x sub n equals b, we'll see that our sequence is monotone increasing whenever b is positive, or monotone decreasing whenever b is negative. Either way, we have a monotone sequence. We have seen that this sequence diverges. Next, let's consider the sequence that's defined more or less in terms of a geometric series. That is, x sub n is L plus x0 minus L times rho to the n. We prove that this sequence converges whenever rho is between 0 and 1 by defining a new sequence t sub n, which is the absolute value of xn minus L. We found that this sequence in terms of t sub n is a monotone decreasing sequence. In fact, the sequence has a lower bound, and one can prove that this sequence tends to 0 using the monotone convergence theorem. In particular, given a positive epsilon, there exists a delta such that t sub n is less than epsilon whenever n is greater than delta. But this actually implies, by our definitions, that our sequence x sub n tends to the limit L. Today we're going to discuss how to apply the monotone convergence theorem and actually computing some square roots. Let's recall some of the ideas that we've discussed in the past. Let F be a complete ordered field. We've seen that the square root of p exists whenever p is greater than or equal to 1. We did so via the following proposition. In general, say that d is any non-negative number in our complete ordered field F. Then its square root exists. Here's why. We'll break this up into 3 cases depending on d. If d is greater than or equal to 1, we'll set p is equal to d, and then consider the supremum over those positive elements in F such that t squared is less than or equal to p. If d is between 0 and 1, we'll define p as the reciprocal of d, and then define the square root of d as the square root of p divided by p. If d is 0, we'll just define the square root to be 0. But how do we actually compute these square roots? We'll do so by defining a couple of sequences. For the moment, let's say that p is greater than or equal to 1. We'll define a sequence t0, t1, t2, and so on recursively in the way that you see here on your screen. When t0 is 1, we'll then define tn plus 1 recursively as p times tn plus p divided by tn plus p. We actually see a couple of relations. First, each tn is greater than or equal to 1. Next, tn plus 1 is greater than or equal to t sub n, and t sub n squared is less than or equal to p. But we have a stronger statement. Given if t sub n squared plus epsilon is greater than or equal to p, then at the next stage, t sub n plus 1 squared plus 1 plus 1 over p times epsilon is greater than or equal to p. The idea here is that if epsilon is small, then 1 minus 1 over p times epsilon is even smaller. In other words, the first bullet point here says that we have a monotone increasing sequence. The second statement says that tn squared is as close to p as we wish for it to be. Again, we know that tn squared plus epsilon is greater than or equal to p for some epsilon large enough. But now the idea is that 1 minus 1 over p will bring us even closer, that is, tn squared will be even closer to p. So, our tn squared can be as close to p as we wish for it to be. We then conclude that our sequence t sub n converges to s, where s is the square root of p. Using the monotone convergence theorem, this actually does give a rigorous proof that s is the square root. We have a similar statement now using decreasing sequences. Let's define a sequence b0, b1, b2, and so forth in the way that you see here on your screen. We'll start with b0 equals to p, and then define recursively bn plus 1 as 1/2 b sub n plus p over b sub n. Now we have a sequence b sub n where each b sub n is less than or equal to p, and also b sub n plus 1 is less than or equal to b sub n. Finally, b sub n squared is greater than or equal to p. Similar to the previous proposition, if b sub n squared is less than or equal to p plus epsilon for some epsilon, then b sub n plus 1 squared is less than or equal to p plus epsilon squared over 4p. The idea here is that if epsilon is small, then epsilon squared over 4p is even smaller. In other words, we have a monotone decreasing sequence, where each b sub n squared is greater than or equal to p. And, as stated before, each b sub n squared is as close to p as we wish for it to be. Again, we see that our sequence converges to S, where S is the square root of p. Using the monotone convergence theorem, this does indeed give us a rigorous proof that S here now is the infimum of this set, satisfies S squared is equal to p. As a reminder, here's some numbers to explain what's happening. Notice that we have the t sub n's, which are defined recursively. Recall that this is an increasing sequence. The b sub n's similarly are defined recursively, but this is a decreasing sequence. T sub 0 always starts at 1 and increases to the square root of p. On the other hand, b sub n starts at p and decreases to the square root of p. The previous two propositions give us rigorous proofs of these statements. Now we'd like to skim over the proofs of what's going on here. As a reminder, we have a few statements we'd like to show, let's say to start, by our sequence t sub n. We'll show the very first statement by induction. That is, we'd like to consider the following statement, which is a function of n. Each t sub n plus 1 is greater than or equal to t sub n is greater than or equal to 1, and t sub n squared is less than or equal to p. When n is equal to 0, then we know that t0 is 1, and we know that t0 squared is less than or equal to p, because of course p is greater than 1. On the other hand, we can also compute t sub 1 by using the recursive relation above to find that that is equal to 2p over p plus 1, which we can easily check is greater than or equal to t0. So this means that our proposition p sub n is true when n is equal to 0. Now, let's state our inductive hypothesis, that is that the proposition p sub n is true for some n equals m. We'll consider the next case, n is equal to m plus 1. Since t sub m is positive by the inductive hypothesis, and p is greater than 0, we see that p times tm plus p is positive, and tm plus p are positive. Recall that this is the numerator and denominator. Hence, the ratio, which we're calling t sub n, also has to be positive. Moreover, t sub m squared is less than or equal to p by our inductive hypothesis, so we see recursively that t sub n squared is going to be greater than p. Again, recall that n is m plus 1. Finally, let's take a look at the difference of the consecutive terms, t sub n plus 1 minus t sub n. By using just some simple formulas, we see that this here is also positive. This actually shows that our proposition p sub n is true for n equals m plus 1. So we conclude that the statement must be true for all non-negative integers n. Now let's try to prove the second statement. We'll have to show a few inequalities. First, p minus t sub n plus 1 squared we can express in terms of p minus t sub n, just by substitution of formulas. Second, we see that this is less than or equal to a similar formula times p minus t sub n squared. Third, because we have by our assumption p minus t sub n squared is less than or equal to epsilon, we're able to conclude the formula that we desired. Now let's try to prove the second proposition. Again, we have two statements. We can show the first statement by induction just as before. All we have to do is verify for the base case when n is equal to 0, which isn't very hard to do. Recall that b sub 1 is equal to p plus 1 over 2, and it's easy to check that this here is less than or equal to p. Hence, the proposition is true when n is 0. We can state our inductive hypothesis that the proposition p sub n is true for some n equals m. Now we'll assume that n is m plus 1. As before, we'll start to write out some formulas to realize that b sub n squared minus p will be the ratio of two positive numbers, therefore it's a positive number. By looking at the difference of the consecutive terms, in this case b sub n minus b sub n plus 1, we see that this again is the ratio of two positive terms, therefore it's positive. So we do conclude that we have our decreasing sequence. Hence the proposition is true for n equals m plus 1. So we conclude that it must be true for all non-negative integers n. Finally, we'll show the second statement. The idea is that we have to show a few inequalities using some substitutions. We can compute that b sub n plus 1 squared minus p is the ratio of two positive terms, but we can actually write this as being less than or equal to b sub n squared minus p quantity squared over 4p. This is by carefully staring at our denominator. But now, for the numerator, we use the idea that b sub n squared minus p is less than or equal to epsilon. So we see that our b sub n plus 1 squared minus p is less than or equal to epsilon divided by 4p. This concludes the proof. As a recap, we now have two different sequences, one involving t's that is an increasing sequence, which terminates at the square root of p, and the second, we have a sequence involving the b's that is a decreasing sequence that terminates at the square root of p. Thanks very much for watching.